Okay, hello everybody. So I took a screenshot of our previous video on the derivative, and I just want to focus on this piece right here. So this is the limit definition of the derivative. So the derivative is going to be a map. It's a linear version of our original nonlinear map, curvy map, and it's going to be a flat version of it. And it's defined as this limit, and we need to understand this. F of p, or x plus hv, minus f of x divided by h. And we're going to let h, which is a little real number that we're scaling down, go to 0. This top numerator will be a vector, and the bottom will be a number, and we need to understand it. So let's go to GeoGebra. GeoGebra Classic. Let's just stay in the plane at first. So I'm going to create a curve. Let's say f equals a curve, and let's make it an ellipse, like 5 cos t, comma, the second coordinate function will be, let's say, 3 sine of t. And we're going to let t vary from, like, let's say 0 to 3. It would look like that. Could go to 4, could go all the way to 5. We're going to get the whole ellipse if we keep going. Let's actually just go to 3. Or we could go to 2.8. I don't know. That'll be enough for us. And now let's create a slider, S. Or no, actually, instead of S, let's make it P for the point P. And so then we can look at, what's f of P? So there's f of P. And, f of, I guess, 2.1 is about there at this point. We could also view this, as the vector. Instead of a start and end point, we can just say the vector f of P. And you see that it's really the same data. The point f of P and the vector f of P are sort of the same, so we'll just use the point. And now what's the derivative? So let's just take f prime of P. Okay, so that's the point, but we actually want to think of the derivative as a vector. So in this case, let's do f prime of P. This is like the velocity of our curve f. And that's what it is. Now the question is why? Because we have this formula. This is what's giving us that derivative. That velocity vector is somehow coming from this limit formula. So let's look at what this is. So let's call it v for velocity vector, and we want to figure out how did this come from a limit. So first, let's just do f of p plus, well, let's make a slider h. H will go to 0. So I'm going to say that h will, maybe it goes from 3 to 0. Or from 1 down to 0. We're going to shrink it to 0. And that is the h in this limit. As h goes to 0, we're going to move in some amount, and we're going to shrink the vector by this real number. So that's h. Now, what is f of p plus h minus f of p? So that's interesting. That's that point. Let's even just take, what's f of p plus h? So f of p plus h is over here. So as I shrink h, f of p plus h is going to get closer and closer to f of p. When h is 0, then they're identical. They're on top of each other. So now we can look at, well, let's say final minus initial. Let's look at the vector going from a to b. Well, that vector is a vector f of p plus h minus f of p. And so now we see that vector there. So as I change h at first, when h is big, the vector from a to b looks like this. Of course, I moved it over here. By default, it has its tail at the origin. But as I shrink b, look what happens. Well, obviously, b is getting closer and closer to a, so my vector, f of p plus h minus f of p, which is the numerator of this, the numerator is a vector. Its top number is a vector. Sorry, it's not a number. This top formula is a vector. And it's getting smaller and smaller as h goes to 0. And that's a problem because, you see, it's not giving me the vector v. It's getting too short. When h goes to 0, it's literally the 0 vector. It's completely disappeared. When h is a little big, so in other words, this vector is too small. That is why we divide by h. And when we divide by a little number, it makes the vector bigger. And so when I instead take the vector let's say, I guess W equals vector f of p plus h minus f of p, but now I want to divide by h. Here's that formula. Now you see I get a different vector. It's this W vector. So there was my previous one. Let's even make this one. This one is going to shrink to 0. Let's give it a color. How about red? And that vector is not so good. It's definitely giving me sort of a change, and as h goes to 0, it's going to give me an infinitesimal change. So when h is big, now h is shrinking, and that top vector is going to 0. But my bottom one, this is W vector, this is the limit vector. So I'm rescaling by h, and that means it won't shrink to 0. It's going to perfectly approach the vector v, which is the velocity. So this is, you can just visually see the formula working. As h goes to 0, my formula here, the change in output vector divided by a real number that shrinks, is giving me the infinitesimal change, or the velocity. And that is how the velocity is really this limit. Okay, so yeah, I just wanted, all you should take away, you're not going to understand all these formulas yet, but now you can visually see this limit formula is indeed giving the correct velocity vector. Of course, we could, when we write a vector, we can write it as a point, so it starts from the origin, goes out to that point, or we can give it a start and end point. Of course, if I start it, so let's do it, let's start it at f of s, and let's end it at f of s plus the velocity. And that will, oh wait, not s. I used p, my slider was p, right? That was the number. So I need to change this. This should be a p. This, should be a p. This should be a p. There we go. Now so this is just the velocity vector, but shifted so that it begins at the point f of s, or f of p, and it goes away. Well, anyway, hopefully this was helpful. I will save this. I will save this as limit definition of derivative, or maybe a velocity vector, which equals, or is a special case of the derivative, just for curves.